So in this video, we will be visiting one of the most important models that we will be talking about. That's the linear model. And we will be using the linear model to perform classification. So the linear model is the most important example in the parametric space of models. So parametric models are essentially models that uses parameters, numbers to define its behavior. So let's recall from the last video, we were using this diagram to explain that it is actually possible when you have a classification task that you want to classify one of three classes, as we see here. You can actually just stack up a bunch of regression functions and identify which of those functions will be given essentially the highest score. The category, the class that would be associated with that high score would be the one that would be picked by our classification function, by our classifier. That would essentially just be picking up the index associated with that class, that specific class. And here you see that our classifier is picking up the class with the label 2. If we simplify a little bit this idea, going back to the binary classifier, where you only have two classes, and we apply a normalization, which is just the idea of having the scores, the sum of the scores being equal to 1, we can actually have a very interesting simplification of the model, because when you have these two scores here summing up to 1, actually, you no longer need one regressor for each class. You actually only need one regressor. And the reason for that is because you know that the sum of the two scores would be equals to 1. So if you have access to one of those scores, essentially, you can have automatically the value of that second one. In this example here, let's say our class 1, the one in the black circle here, let's say it is giving the score of 0.75. This automatically means that that would be the class that would be chosen. That would be the output of our classifier. Another way to think about that, or to explain why that class would be the picked one, is just by applying a threshold. So the threshold is really just checking if the score that you are inspecting is greater than 0.5, because we know that the sum of the two scores, you only have two classes, right? So the sum of the two scores would be equals to 1. If you have a score that is greater than 0.5, automatically the other score will be smaller than 0.5. So you can just apply directly that threshold. If you have a score that is greater than 0.5, that means that these would be the class that would be picked. So normally we would apply the regression function to the one class, which means that the output of that one class, every time that it is greater than 0.5, it's classified as 1, as class 1. This is just explaining the same idea, and the idea of the thresholding. So these would be a very important concept that we would be visiting a lot of times during this course, and specifically about in this video. And as I mentioned before, if you want to know the score of the 0 class, the class that is represented by that blue circle, you can just get you can just subtract the score of the 1 class from 1. So automatically you would be able to access the score of the first class, the class with the label 0 in this case. So I told you that the linear models are the most important parametric model. But when we say parametric, what does that really mean? So parametric means that we are using numbers that would be part of the definition of the model and also the learning of the model. So in other words, when I train a model, I am essentially making the model learn an optimal set of values, and those sets, those values would be my parameters. So essentially, if I set the parameters, I define my model. If I want to learn a model using some training data, I essentially would be finding the best possible values that I can for those parameters. So that's what this parametric refers to. The opposite idea would be the non-parametric models that do not have that learning behavior. So these models would be defined in different manners. And the next model that we would be visiting, the K nearest neighbor classifier, would be one example of a non-parametric one. So let's continue with our understanding of the linear model. So here on the right-hand side, you see that you have a sort of a plane that you can see that lives inside these three-dimensional plot that you see here. So if you check here, the axis in the bottom, that would be my y and x axis. So these two axes represents my inputs, and my vertical axis here would be my f of xy. So that would be my scoring, my output of that linear function. So because I have two inputs, my inputs are represented here in this equation by my x and my y. You see that this plane here is a hyperplane. And the idea of the hyperplane is just the idea of an n-dimensional plane that lives in a space that has one more dimension, or equivalently, coming from a three-dimensional space, if you have a two-dimensional object, that can be thought of as a hyperplane. So hyperplane is what essentially is the geometrical understanding or description of a linear function. A linear function can have as many inputs as as your data set allows, or your choice of inputs. And the more inputs you have, obviously, the more dimension that hyperplane would have. So one way to think about these is precisely how you are seeing here in this diagram. So one way that I like to think about it is by imagining that this is a sheet of paper, and you can tilt in many different ways that paper, and that tilting essentially is the way that you are defining that model. When you choose a set position for that sheet of paper, that would be your model. So the coefficients that you see here in that equation, in this case, the 2 that is multiplying my x, the -3 that is multiplying my y, and my 4 that is not multiplying any of my inputs, those would be the coefficients, those would be the parameters of my model. So this defines my model. So that's what we referred to a while back as the parametric meaning of those models. So another thing that would be interesting to mention is that this scoring function, my f of xy, my hyperplane, in this case, goes from -infinity to positive infinity. So I have most likely my input living in a infinite range. That's not always the case, but that's what it looks like in this case here. And also my scoring function equally would be giving me a range that that would obviously depend on my inputs, but most likely would also be varying from -infinity to positive infinity. So how do I use a criteria to make my classification based on this hyperplane, based on this geometrical understanding? That's what we would explore in the next slides. So here, as I mentioned, you see that the 2 and the -3 and the +4 would be the coefficients and the bias that would be defining that linear model. So one way to understand the intuition behind that hyperplane is that the coefficients, essentially my numbers that are circled in red here, they are essentially determining the angles that my plane would be doing with respect to my origin. And my bias would be a shifting that would be happening. So you can think of it as just moving that hyperplane, again, using the example of the sheet of paper, moving that sheet of paper up or down would be equivalent of you incrementing or decrementing the bias. So that's what we are seeing here in these examples. And the output, as we have seen before, in that initial example that I have shown, the output can be used to evaluate if the score would be beyond that 0.5. If it is beyond that 0.5, then I can actually use that as my threshold that would determine the classification outcome. So the hyperplane itself is a regression function, right? How do we do the classification? By applying that threshold. So you apply the threshold, and anytime that you see a score, the output of that f of xy being greater than 0.5, you would be classifying that specific point, that specific input, as class 1. If you see that score being smaller than 0.5, you would be classifying that as class 0. And remember that we only have classes 0 and 1. This is a single function. So we, even though we have a binary problem here, we can and also because of the fact that we are representing the classes as zeros and ones, and in the data set you need to have that. So that's one important observation that I want to make. In your training data, you need to make sure that the representation of the classes are as zeros and ones. Otherwise, this threshold will not be precisely at 0.5, because that's the midway between the values of your two classes. So here we have a few examples of inputs that we would be using for this model. So again, as I mentioned, as soon as you have your weights, your coefficients, and your bias, this precisely defines a model. So now you can use any input. So you can just plug in values for your x and y's in this case. And that's what you see in these examples on the left here. So for instance, if I am checking, if I am using the input as my origin, as my 0, 0, I would be just plugging in here my 0 on the left-hand side for my x, and my 0 for my right-hand side for my y. And I would be multiplying those two zeros by those coefficients that I have here. My bias do not multiply by any input. So then, because I'm at the origin, essentially, my output would be equivalent to my bias. And that's always the case, no matter what linear model you would be checking. Every time that you check, that you use as input the origin, that means that you are setting all your inputs to 0. So then the output that is going to be given out by that function would be equals to the bias. And you can see that right here, right? And you have those examples when you have the points 1, 1 and the points -1, -1, and that would give you values for that output. So in all these three cases here, you have scores that are greater than 0.5, right? So this means that if I apply my classification rule, I would be classifying those 3 points as class 0. Sorry, class 1. All right, another interesting way to represent this process is by using vectors. So I can use a vector here on the top. You see that I am calling the vector of coefficients as beta. So the beta would be storing the bias, typically as the first number in my vector. So if you see here, I have a beta 0. That would be my 4 that comes from that formula here. And I have my first coefficient that would be equivalent to my coefficient that is associated with my x input. And then I have my second coefficient, my beta 2, that is associated with my y input. So these two things, as you see, are using essentially two different notations, but they represent the same thing. So my beta here is carrying the values of my coefficients. What about my inputs? So we typically also use vectors to represent the inputs. In this case, there's one important observation here, which is because of the way that we have set up our coefficients, by including the bias as the very first element that we have here, I need to necessarily put a value of 1 in the equivalent position in my inputs. So my x0 here essentially is a constant. It's just the value 1 that would be always equals to that constant. It does not change, right? Because it does not actually depend on my input varying. So if you would actually have multiple inputs being used in the model, every new input would always have that position set to 1. In terms of vector operations, we can represent the f of x, or the output of my model, as a dot product between my x vector here and my beta coefficient vector. So if you see that in a matrix form, I can also represent that in terms of the multiplication of x transpose by b. This is needed to be done because if you are multiplying, as you know, you actually cannot multiply two vectors with the same dimension, right? Unless these are 1-by-1 vectors. So you need to turn your x input into a row vector. So then you can do this dot product operation as a regular matrix operation, right? So this is just different ways to represent the same idea. So the dot product between these two vectors is the same as having the multiplication of the row vector version of your input and the column vector version of your coefficients vector. So this is also equivalent of showing in this form here, if you see all the terms, and that essentially is the form that we have shown here in the first place. All right. So if you have, for instance, an input of -1 and -1, you would be essentially plugging in those values in that formula, and you would be getting your output, in this case, equals to 5. So as we saw, the general formula that we can use to a linear model is essentially saying that our y hat, that is the output of my linear model, would be equals to my beta 0, which is my bias, plus a summation of the beta j times my input j, summed over all the inputs that I have. So if you have, let's say, 10 numbers as inputs, 10 features, you would be doing that 10 times plus that summation 10 times plus the bias. And the other way that you can represent the same idea is in the matrix form. So you can also represent in a more short way, and actually that way is even more popular to be used because it's more short. It conveys the same idea in a shorter form. And again, remember that if you don't have the bias in an explicit manner, as we had in the previous slide, you would need to use your x, including that constant 1, if you have the bias incorporated into your beta coefficient vector. So how do we create a linear model? So creating a linear model is nothing more than just choosing numbers for the coefficients that define that linear model. So it's as simple as choosing the values for beta 0 and beta 1 and beta 2, in this case where I have two input features. So let's say you have this input here. How would you tell what a good choice of a beta would be, of the values that would comprise my beta would be? What do you think? So let's go back to our framework of what a machine learning problem is, right? So we need to specify a task, a performance metric, and a source of training, source of knowledge. The way that we are going to go about our learning problem would be by defining that our task would be to score by using a linear model, so a linear function in that form that we have seen for the class 1 for inputs that that are in RP, meaning that you have an input space that is p dimensional, and p is just the number of features that you have. So if you have, as in the example that we have seen before, if you have 2 inputs, so then p will be equals to 2. So then that's a 2-dimensional real space. We would be inferring the optimal weights. So my optimization objective can be described as just finding the optimal values for my weights that comprise my beta vector. And my performance metric that I would be using would be a very popular one. This is called the residual sum of squares. So the residual sum of squares is the idea that you would compare the difference between the values that you see in the training data and the values that you see that are generated from your function. So there's a delta there, right? So there's a difference. You're going to essentially square those values, and then you're going to sum up all those values. So that's what defines the objective function, that is the residual sum of squares. And we would be seeing the formula of that one in a bit. So what we want to do essentially is to have the smallest possible error, right? So this is a minimization objective. So I want to essentially minimize my RSS, my residual sum of squared errors. And the way that I will find, finally, my RSS in this case is by using calculus, because this is not a general thing, but because of this RSS objective is a concave function, you can actually use calculus to just find a closed form solution for that minimization. So again, this is not something that you would have on any machine learning model. And actually, most models, you would not have that ability to directly calculate what the optimal values for your beta, for your coefficients. But in this case, it's convenient because we can do that. And that's one example that we would explore. So here in this slide, you see a representation of your scoring function. So in this case here, we are generalizing. So as you see, this curve here is not even linear, but this gives an idea of what we mean by the RSS. So the RSS again is the difference of the prediction and the actual value. So the actual values are coming from my training data. Because these are values that live in the training data, I can actually visually see those, right? So I can just put, and you see those red dots, red points in the plot here. This represents my samples that I have in my training data. So the value that you see as the score that is expected in the training data would obviously not always match what your scoring function would be giving. So there's a difference between the red point and the actual prediction that your scoring model is doing. So that difference would be essentially squared and then summed over all the points that we have. So if you have a data, let's say a training data set with 100 points, and you are using that whole set for training purposes, this means that you would essentially be summing up the errors over all these samples. So this is the formulation more formally of my RSS objective. And here, as you see, we are minimizing the beta. So that's our goal here, is to find the beta that would give the smallest possible RSS value. And as I have mentioned before, you have here the X times beta, which is just the linear model output itself. So my model is producing as the output precisely that amount. And I am just subtracting that by my yi, which is my actual value that I see in my training data. So I do that I calculate that difference, I square that difference, and then I go over all the training samples that I have. So that's what this summation here is essentially doing. So visually, it's easy to see that because this is a quadratic function, you would have a single minimum. So you don't have many minimum values in that curve. You have one single minimum, and then you can just take the derivative, set it to 0, and then you would be able to find the closed form for your optimal RSS. Your optimal beta according to the RSS criteria. This slide is just showing that. So a way to represent in terms of matrices and vectors, my RSS. So this is precisely equivalent to that previous formula that we have seen. If you differentiate with respect to beta, set that derivative to 0, you would be able to find the closed form for that beta. So that would be your beta hat. That's how we are representing here. And if you want to check out in more detail, you can check this link to see the step-by-step derivation of that equation. So visually, what we have here, this is another example. Obviously, we don't even need to describe what that data is representing, right? But we are seeing here that based on this plot, we have 2 dimensions. So I have 2 axes here, and I have my data points being represented by these circles. So I have a couple of orange circles and a couple of blue circles. The color of the circle itself is the actual value, the actual label of that data point. So these circles here are essentially all my training data points that I have available to me. But then you see that you have these line here, this black line. This line, we refer to that line as our decision boundary. And that would be a very important concept, and we would be exploring a lot of examples on that. We would be doing our upcoming exercises, our problem solving, and our programming assignments. So this idea of decision boundary would be explored a lot on the coming assignments. So again, continuing on my explanation here, we have the circles representing essentially the color of the circle representing the actual label, but you also see a sort of a shade here, right? So these small dots here, if you check above this line here, you only have orange dots, and below that you only have the blue dots. So I am referring to this as a orange shaded region and as a blue shaded region. So these essentially are regions that are being defined by my decision boundary. So this line that you see here, this is what is separating these 2 portions, these 2 halves of my space. And this would essentially tell me what the prediction of my model would be, right? So if I have the blue shaded region, if I am, let's say, choosing a point, any point that would be in the blue shaded region, this means that my model would be predicting that point to be blue. In that case, blue is mapping the 0 class, and orange is mapping the 1 class. So I can also say equivalently that anytime that I pick a point that is in the blue shaded region here, my model would be predicting that to be a 0 class. Conversely, if you choose any point on the top part of that space, your model would be predicting that point to be of the orange class, to be of the 1 class. So do you see why it is so important to think in terms of the decision boundary? If you observe the decision boundary, you can tell right away what the prediction of the model will be. So it's a very easy, it's a very common and a very easy to use tool that you have for any model really. So this does not apply only to linear models, but to any model when you have the input space and you have your decision boundaries, so you can right away make sense of how the model is essentially doing its work. Here we have an example here using NumPy. So NumPy is a library that we would be using a lot. In this example here, this is actually taken from the example that we would be using in our first programming assignment. We have the features, the feature values, and then we have the class, the associated class for that given input. So how do we actually calculate our decision boundary? So remember that we have mentioned before that our model, our classifier, is essentially applying a thresholding, essentially just checking when the score is going above 0.5. So you can actually use that to visually see where your decision boundary would be. So if you set your x times beta to 0.5, that would be precisely on the decision boundary. That's the line, in this case a line, because my input space is a two-dimensional space. So recall that we have a hyperplane always one dimension less than your space. In this case, this two-dimensional space has a hyperspace of a hyperplane of a single line. So if you check here, you can just see that all the points that would be sitting on that line would be having the score as equal to 0.5. So that's how essentially you determine, or how you draw, how you identify where your decision boundary would be. And this is just to recall that that thing that we have mentioned before about the decision boundary. So another thing to make sense of that is that recall that your scores, because your inputs lives in an infinite range, your scores would also go from minus infinity to positive infinity, right? So we know that every time that you go that you go far from the decision boundary, roughly in that direction, so that would be perpendicular to your decision boundary, as you see here. Every time that you go perpendicular, you would be going towards the direction of the increment. So that's because the orange here is the one class. So that's always happened on the one class. Depending on the data set, obviously that's not always the case, but as soon as you identify the half of the space that is the one class, so you can have a sense of how or in which direction your scoring function is actually increasing. And that would be essentially by going away from your decision boundary. So the same idea you can apply the other way around. So if you want to actually make sense of when your score is decrementing, you can just move in the space, the half space that is defined here by that blue region, or the region that would be the zero class. And that's the same idea that we have explored at the very beginning of our demonstration on the linear models. So let's explore a little bit more on the intuition of our hyperplane. So here you see that I have my axis here. My beta 1 and beta 2 would be obviously associated with my my features 1 and 2. So recall that the coefficients are multiplied by the inputs, and then I have my scoring axis here, and that would be associated with my bias, with my beta 0. So if I have a model that is defined by these beta that you see here on top, 0, 0, and 0, what you're going to have is essentially a hyperplane that would be sitting, would be intercepting the origin, and it would be parallel to these two axes, my input axis. So again, if you think of the hyperplane as a piece of paper, as a sheet of paper, that's essentially the idea, right? So if you have a sheet of paper that sits essentially flush against a table, for instance, so that would be the idea of the angle that this hyperplane is essentially doing. So another example that we would see here is by changing the value of the bias. So if I just change the value of my bias, I'm essentially just pushing down my hyperplane. So this means that the values in which my score would be 0 would be lower in this axis of the beta 0. So another example here that we see is if we change, for instance, our first feature. So in this case, we are changing the beta 1. So we will be tilting a little bit our beta. In this case, we are applying a negative coefficient. So this means that you would see essentially the reverse in terms of the scores with respect to your input. So because this is with respect to your x, your first feature, right? So then every time that your x goes below 0, you'd have a score that goes above 0 because your bias is 0 and all the other coefficients are 0. So just by looking at that one coefficient, you are able to make those rules. And when you have your x equals to 0, so then obviously your score would be 0, right? Because the hyperplane is going through the origin. And if you set the input to 0, that'll be 0 times -1. So that's 0. So the same idea can be applied. So if you have now both the bias and my x as -1, so now my bias, recall that my bias being -1, it was equivalent to pushing down my hyperplane, and the tilt that we have mentioned in the previous line would be the -1 applied to my beta 1, my beta 1 axis. So then you could make these sort of claims with respect to your input. So when your input is smaller than -1, so recall that before we had as the threshold the 0. Now because my bias is at -1, my threshold now is at -1. So every time that you see the x smaller than -1, this means that your score would be going above 0. And the other way around is also true. And if you have your x equals to 0, so that's similar to what we had before, but because my bias now is -1, so then when all my inputs are 0, my output, my y hat, would be equals to my bias, which is -1 in this case. All right, so as the last question that I want to leave for you to think about in this video is we are defining here our model by using the RSS criteria. So we have these as the closed form to give us the beta, right? So that, by the way, this plot here is precisely the beta calculated for the minimal RSS. So this is precisely what you see in this plot here. So how can we tell how good this boundary is? Is there any way that we could actually have better boundary than what you see here? What do you think? So put in the Discord what you think about that, and let me know if you have any questions. So I'll see you in the next video. Bye-bye.